Now let's talk about the moon. The moon is a prominent object in the night sky, famous in astronomy, famous in myth and culture, and obviously known throughout human history. Lunar motion is important, not just for astronomy, but for human culture. The phases of the moon reflect how long it takes the moon to complete one cycle of its phases. And this is called its sidereal period, which is the actual time it takes the moon to orbit the Earth. The sidereal period is 27 1/3 days. The synodic period, which is the time of a full set of lunar phases, is a longer number, 29 1/2. And it's this alternation of 29 and 30 days that reflected the first lunar calendars used thousands of years ago. Let's look at the phases of the moon. The sunlight is coming in from the left, and you can see that the moon is always half lit by the sun, as the Earth is. But our view of the half-lit moon depends on the angle between the Earth, moon, and sun. And that is, of course, what reflects the phases of the moon. If we look at it again, when the moon is away from the Earth relative to the sun, we see its full lit surface. When it's between the Earth and the sun, we see its dark surface. Hence new moon, hence full moon, and in between first and third quarters. A full cycle of moon phases, 29 1/2 days. Here's a different way of looking at the model. This is just a simple model you could do yourself. Create a light source, make yourself the Earth, have a polystyrene ball as the moon, and look at what it looks like to you as you make the moon orbit you. The moon orbiting the Earth, the sun far off to the left, and you will see the lunar phases the way we do. Highly recommended. Here are the moon phases animated in the first quarter on the top left, second quarter, top right, and the other two quarter phases, showing the continuous variation in the illumination of the moon. Lunar motion. When the moon's orbit intersects the ecliptic, which is called a node, at new moon, we can have the possibility of a solar eclipse. But you must be in the moon's shadow to see it. At full moon, we have the possibility of a lunar eclipse, and that can be seen by almost anyone on the night side of the Earth. And as we look at the geometry, you'll see that the solar eclipse geometry is far more specific and precise, and so solar eclipses are far rarer than lunar eclipses. Most people have seen multiple lunar eclipses in their lives, but many people have never seen a solar eclipse. Or if they've done so, they probably had to travel quite far to see it, or see more than one. I'm lucky enough to have seen 6 solar eclipses. I have colleagues who've seen 30 or 40, which is amazing. They're quite special phenomena, of course. And if you get a chance to see a solar eclipse, you should do it. So let's talk about eclipses and where they come from. Here's the geometry of the lunar eclipse, so let's look at it. As the moon is on the far side of the Earth relative to the sun, and remember the distances in this animation are not to scale, we see that the Earth will cast a shadow into space, always from the sun, and if the moon passes through that shadow, then the moon darkens. Outside of the shadow, of course, we're seeing the half-lit face of the moon clearly, and the moon is essentially a full moon. But as it passes directly into the shadow, it's in darkness. Now there's a little scattered light, which is represented here as red, and indeed a lunar eclipse, it does look red because it's scattering light through dust in the atmosphere, reddening it, but much dimmer than when it's outside the shadow. You can also see that because the moon is smaller than the Earth, it occupies a small fraction of the Earth's shadow, and that's important too. And so because of this geometry, you can see that anyone on the night side of the Earth should be able to see a lunar eclipse quite easily. Solar eclipse is much more particular. That occurs when the moon passes between the Earth and the sun. And you can see that the moon casts a shadow which makes a rather small spot on the Earth. The full darkness or umbra spot is about 70 kilometers across. And this spot will track across the Earth due to a combination of the Earth's spin and the moon's motion. And so at one point on the Earth's surface, here you're seeing the Great North American Eclipse represented, at one point on the Earth's surface, you would have to be very lucky to see a solar eclipse because it occupies the shadow, such a small fraction of the Earth's surface, and also it's a very transient event because that shadow is passing across the surface of the Earth at hundreds of miles per hour. And so you're only in the shadow for a short period of time. Typically, solar eclipse will last 3 or 4 minutes of totality. I think the longest ever is about 7 minutes. These are the solar eclipse geometries. And because of the variations in the Earth-Sun and Earth-Moon distance, the alignment is not perfect. In other words, you don't reach the perfect point of the cone of the shadow on the Earth's surface. And so typically, you can have a total eclipse where you're entirely in the umbra or the darkest region of the shadow, but also you can have a partial eclipse where you're in the penumbra or partial shadow. And that's actually a more likely circumstance. In terms of frequency of eclipses, they don't occur every month. If the Earth and the Moon and the Sun all occupied the same plane, and the Moon was going around the Earth, then obviously every 2 weeks it would pass between the Earth and the Sun, and you'd have a solar eclipse, and 2 weeks later the Earth would pass between the Sun and the Moon, and you'd have a lunar eclipse. But they don't occur every month each, and so we know that's because they're rare. And they're rare because of this geometry, where we see that the tilt of the Moon's orbit around the Earth by about 4 degrees means that the alignment has to be very particular for it to get either a solar or a lunar eclipse. And it typically only happens at the nodes, which are the regions in this orbit represented here at the top and the bottom of the diagram. Those are the positions when you can get eclipses. 3 months later or 3 months earlier, you can see that the tilt of the Moon's axis around the Earth means the shadows are cast into empty space, and so you do not have the configuration that leads to eclipses. Here are some of the maps of the eclipses of the recent past moving into the future, and you can see the paths that the eclipse takes, the solar eclipse, across the Earth. Again, the shadow moving very quickly and not, of course, covering more than a small fraction of the Earth's surface. Hence, you have the situation where lunar eclipses are fairly commonplace, have seen by everyone, but solar eclipses are quite rare. And you can look at this map, which represents solar eclipses over almost half a century, and realize that in a human lifetime, which for most of history was less than half a century, you would have to be very lucky to live in a place that had a solar eclipse. So solar eclipses were occasions for awe and mystery and even fear, because they were so rare and they were so dramatic. When the sun is eclipsed or occulted by the moon, the temperature falls by 10 or 15 degrees. Animals think it's night and get disoriented, and it's a very unsettling thing to an ancient culture that did not know what was going on. Let's look at the planets in the sky. The planet, as I mentioned, is from the Greek word for wanderer, because the planets appear to move across the fixed pattern of the stars. And we can divide the planets into interior planets, which are the planets between us and the sun in their orbits. Now, for ancient cultures that didn't know the distance or position of the planets, they noticed this simply as the planets which never appeared very far from the sun in the sky. Mercury, for example, is always within 15 or so degrees of the sun, and Venus about twice that angle from the sun. So if you want to know where to look for Mercury and Venus, the inferior planets, you have to look close to the sun in the sky, and you can probably only see them just after sunset or just before sunrise. The superior planets are the ones further out: Mars, Jupiter, Saturn. In the ancient times, these were the only 3 planets. Neptune, Uranus, and Pluto were added later using telescopes. And so the superior planets are further out from the sun than the Earth, and they have orbits that take them all over the sky, so they can be seen at any point along the ecliptic. Because the solar system orbits in a plane, the sun, the moon, and the planets all occupy a same strip of sky. Not exactly a line, that's the ecliptic at the sun's orbit, but a sort of band. And that's that band, of course, that gives us the constellations, the zoo of animals, and the zodiac. There are also definitions: conjunction, which is the geometry you see at the top; maximum elongation, which is the maximum distance of a planet from the Earth; and opposition, when it's the furthest away from the Earth relative to the Sun. These are ways of keeping track of the planets relative to the Sun that amateur astronomers use all the time. A very particular phenomenon, of course, is the retrograde motion of Mars, also of Jupiter and Saturn, but much more subtle. Here's a time lapse of Mars on the sky showing its motion with respect to the stars over a several-week period. Now this happens every 2 years as Mars recaptures its same place relative to the Earth in its orbit. And it's a remarkable phenomenon because usually the planets all migrate in the same direction through the fixed patterns of the stars. But you can see that for a period of time, Mars appears to reverse from night to night and then recapture its original direction and then continue in that direction. And then that same little episodic backward motion, called a retrograde motion, will appear 2 years later. This phenomenon, of course, was well known to ancient people and ancient astronomers because Mars is a very easy to observe object in the night sky, and it was mysterious to them because there was no obvious explanation. The quirks of the planets, their motion among the stars and this retrograde motion, were deeply mysterious and unsettling because nobody knew how to explain them in antiquity. We can now explain them because we know that the Earth moves inside Mars on its orbit of the Sun, and it moves at a faster speed. And in these animations you can see that what's happening is that as the Earth overtakes Mars on the inside track, if you like, and you look towards Mars in the night sky, its position projected onto the stellar background appears to momentarily reverse direction as the Earth overtakes the planet. You can see it in 2 different versions. And because the Mars orbit is tilted relative to the Earth's orbit of the Sun, that motion doesn't backtrack on itself directly, but forms a sort of an S shape on the sky. So this is retrograde motion that literally has been known for thousands of years. All of these phenomena of the night sky are things that you can discover for yourself. And so as we finish this section and this module, I want to encourage you to go out and actually see all these things, none of which need a telescope. All of these phenomena, okay, solar eclipses, that's a little hard to go out and see, but almost everything else I've talked about are things you can see in an average month or a day or a night or by careful observation over a year. They were known to almost all the ancient cultures of the world and were objects of mystery and enigma and, of course, storytelling and myth and legend. So whether you have binoculars, you don't need a little telescope or a large telescope, you just need the naked eye and a moderately dark sky. So I recommend you go out and look for yourself. And that's the end of this module.